Good day and welcome to theme 3.5, where we will be discussing rotation and divergence of a vector field. So, divergence of a vector field is basically, it describes the net rate of change of the mass of fluid flowing from a point per unit volume. That is just the big words of it. Basically, it tells us how much that vector wants to move from a point. Doesn't want to stay there, doesn't move quickly, or that's basically what divergence of a vector field tells us. And it is calculated by the dot product between del and a vector field. So del is just the partial derivatives towards x, y, and z in a vector format. So it just looks like this. And then you get a scalar function, because if we have a dot product, we sum them together. If our divergence of our vector field is 0, that means that f is incompressible, which just means that it isn't changed and it doesn't really move. If the divergence of f is greater than 0, then x, y, z is a source. So that just means that it really wants to diverge from it. If the divergence of your vector field is less than 0, then it means that it really doesn't want to, and it just stays there. It moves into the point. So it's like a sink. And then our next is the rotation or the curl. Curl is the more used name for it, so we'll stick with the curl of f. So it's basically just a measure for the rotation of fluid around a point. And it's determined by the cross product of del with the vector field. So you still have del, but it's cross producted with p, q, and r. If you remember how cross products work, you have this little table of I, j, and k. Remember to write I, j, and k, just so that the lecturers know what you're working with. And then p, q, and r. And then for the I, you say d dy times r. So you derive r towards y minus q derived towards z. And that would be your I component. And then for j, you say r derived towards x minus p derived towards z, and then whatever you get here, you say minus that, because that's what we do with j components. And then for the k component, you just say q derived towards x minus p derived towards y, and that will be your k component. And the curl of f, which is a vector. So if the curl of f is equal to 0, that means there's no rotation around that point. So we say that the vector field is irrotational at the point, which just means it doesn't rotate. So some useful relationships is that if the curl of a gradient function vector field is 0, that means f is conservative, because the curl of f is 0. Basically, you can just say that if the curl of f is 0, that means that it is conservative, because the curl of a gradient vector function is equal to 0. That just means it doesn't rotate. It is conservative. The divergence of a curl is 0, because if you have a curl, there will be no divergence, because it will rotate at that specific place. An example for rotation and divergence. Show that the vector field of x, y, and z, which has been given here, is conservative, and find the potential function of f. Remember how I said that for three-dimensional vector fields, we can't really tell how they're conservative yet, but now we've proven a way. So if the curl of your vector field is equal to 0, we know that it is conservative and a potential function of f exists. So first you have to test, is the curl of the vector field equal to 0? So we take the curl of f and we find that it is indeed 0. So f is conservative. Now we find the potential function of f. So what we do is we follow the steps. We say, okay, so the partial derivative of the potential function towards x is y squared cos x. And towards y is 2y sine x plus e to the power of 2z. And for z, it's 2y e to the power of 2z plus 3. So then you take one of those and integrate them. I usually take the partial derivative towards x, but anyone should work as long as you follow the steps. So then you get your approximate f of x, y, z, and you get this g, y, z function. Because if you partially derive this whole thing towards x, this will fall away. So it's like a constant function that falls away as you derive towards x. And then you derive towards y or z. I derive towards y, which will give you 2y sine x plus gy yz. So then you find, okay, what is missing from this part that was given in our vector field function? So in this case, e to the power of 2z was missing. So g partially derived towards y is equal to e to the power of 2z. If you integrate that, it'll give you y e to the power of 2z plus a function of z. This can be an hz. And then what you do is you plug that all into your function again. And then the last step is you've derived now towards y and x, and now you derive towards z. So that will give you 2y e to the power of 2z plus g prime or h prime of z. And then you look what is missing, and it's a 3. And then you integrate this function, which is h, and that would give you 3z plus k. And then you use this and plug it back into your function, and you have your potential function. And that is just how you use the curl of f to determine if your vector field is conservative or not. And then you can use your fundamental theorem to just get the line integral of your vector field.